Okay, welcome back. We are now going to discuss section 1-2, which is all about finding limits. This is one of the first tools in calculus that you'll be using. It's not truly calculus yet, but we need to understand limits in order to derive some of the tools that we will be using in calculus. So section 1-2 discusses this notion of a limit. I talked about limits in the previous video, briefly. But what they are is we use limits as a tool to push on an x value to make it approach a particular x value. And we normally do that on a function, and we try to determine what the output of that function would be when x gets really, really close. So let me talk about this for a moment. So let's say we had a curve that happened to be undefined at this very one spot that we'd like some valuable information. Now you got to see that even though there's a hole there, it certainly does line up with some particular y value. In fact, we're going to label that y value L. Down here is our x equals c, and I got a quick question for you, and that is, what is the f of c? Now you know how to use curves like this. You refer to the function, you look at the x value, you go up, and you pick up the y value, but there's a big open space here. There's nobody home. So f of c is completely undefined. Yes, I see the L over there, but if this were a function that were in your calculator and you plugged x equals c, it would come out and say error. So f of c is undefined. What is a limit going to do for us? Here's what it really does. The limit allows us to creep up on x equals c. And we need to do that from both sides. So we kind of sneak up on x equals c from the left side. We sneak up on x equals c from the right side. And we just ask this question, and that is, I know that the f of c isn't working right now. But where were we headed anyway? Well, as you increase x towards x equals c, the y value is increasing, increasing, increasing. It's really trying to get to y equals L. As you approach x equals c from the right side, it's decreasing, decreasing, the y value is, and it's trying to get to y equals L. So all roads lead to y equals L. So this is the answer to the question, where were you headed in y? Now, I think it's interesting to note that that is truly the question you should be asking. Where was I headed? We actually don't care what the f of c is. I don't care if the f of c is defined. I don't care if the f of c is L, or if the f of c is k or some other value, a million or a billion. It doesn't matter. The question is, for a limit, where were you headed? Not what is the function value. Sometimes it is the function value, but other times it is not. So that's the big question. Where were you headed? Where were you headed? Let's do some of these graphically. If you want to analyze a graph, we can answer that question. So I'm going to give you a graph right here. It's a parabola. Let's make it simple. F of x equals x squared. And right here I'll put a point. 1 squared is 1. And the question I have for you is the limit as x approaches the number 1 on this function equals, remember, it's where were you headed? And you have to agree from both sides. Okay, so literally, to do your limits, I would do this on a graph by coming at x equals 1 from the left side, coming at x equals 1 from the right side, and being in agreement that we are headed to y value 1. Now, it just so happens that the f of 1 on this curve is 1, but remember, I'm going to have to say I don't care really about that. The limit just doesn't care what the f of 1 is. It really doesn't. Sometimes the limit is the function value. So you really have to look at the graph and say, where was I headed? Let's try another one. Now I'm going to put this point way up here at y equals k. I'm going to put this open circle, I'm going to line it up with y equals L, and I'll make this a function, f of x. It is a function. And the reason I know it's a function is because it passes the vertical line test. You can draw vertical lines. Every time I draw a vertical line, it will only touch the function once, including this vertical line here, because it would touch here and it wouldn't touch there because there's no point there. Okay, I've got two questions for you. The first question I have is, let me line this up with x equals c. We normally like to locate our point of interest at x equals c. And I've asked this question, what is the f of c? So I want you to look at that for a second, think about it. And if you were to use this graph, you'd say, well, let me go to x equals c and look up for the answer. Well, there's no answer there. There's an answer right there, though. So the f of c is actually k. Now let me answer this interesting question, which is the limit as x sneaks up or approaches c. Now remember, limits don't care what the f of c is. They don't care what the actual y value is. We have to answer the question, where were you headed? So let's get on this road. And while we're on this road, we seem to be increasing, and we look like we're headed to y equals L. But you have to come from the other side and be in agreement. So let's get on the other road, come down, and it looks like we're decreasing y. It looks like we're headed to y equals L. So to answer the question, where was I headed? I was headed to L, even though the curve jumped up to k at that moment. So that's a really good example of how a limit and a function can actually give you two different answers. So remember, limits answer the question, where was I headed? And it can actually be different than where the actual function is. That must be a piecewise defined function for that to happen. Okay. So that's the way to evaluate a limit graphically. Let's try one more graph, and then I want to look at this numerically. So if I were to have a graph that looks something like this, maybe even a line. Well, that was a pretty good break right there. And if this were my function, and this happened to be my x equals c right here, and maybe this was y equals 1, and up here we'll make this y equals 2, let's start answering some of these questions. First of all, what is the f of c? Well, the f of c is 1, because it's right here. The next question to answer is, what's the limit as x sneaks up or approaches, as approaches c? That would be x approaching c, okay, of my function. Okay, remember how to do this. On a graph, you want to sneak up to x equals c coming from the left side. And if you did that, you would say, well, I'm 1. Not only approaching 1, I just keep saying 1, 1, 1, 1, 1, 1, 1. So I'm headed to 1. But what would happen if you got on this road over here? You would say, well, wait a second. When I'm on this road, I'm headed to 2, and I'm not in agreement here. So what happens is when the left and the right sides do not head to the same y value, we say that the limit does not exist. We shorten that up as DNE. We don't say that limits are undefined. We say that limits do not exist. And they do not exist for a variety of reasons. But one reason is a limit does not exist when approaching from the left and right doesn't match. So that's one reason why a limit does not exist. So we got to be careful. So when you want to evaluate your limits graphically, you want to look at the graph, you want to get on each side of the graph and point your way towards x equals c, and your fingers should be pointing at each other at that moment. Say, I'm in agreement. I came at it from the left, I came at it from the right, and it looked like we were headed to y equals L. Now remember, the function value itself, I don't even care what it is. It could very well be, the function value could be L, it could be something else, the function value could be undefined. Doesn't really matter. Okay. So now we know how to evaluate some of our limits graphically. What other limits fail to exist? That's not the only time that a limit does not exist. Here are a few more examples. So if I were to draw you a curve that had an asymptote, and the curve looked something like this. And this happened to be right where I want some answers, x equals c. Now, the first thing you would probably state is that the f of c is, well, it's undefined. Why is it undefined? Well, because it's heading off the page to positive infinity, and that's just too big to quantify. What about the limit as x approaches c of this function? So x is not equal to c, x is sneaking up on c, and you have to do it from both sides. You really want to go back to the curve and explore that. So we're going to have to get on the left side of the curve and answer the question, where was I headed? It looks like we're headed to infinity. Get on the right side of the curve, say, you know what? From the right side, it also looks like I'm headed to positive infinity. So you know what? We're in a total agreement that we're headed to positive infinity. But wait a second. You see, I wrote positive infinity for the function value, but I backed it up with undefined because infinity is just too big to quantify, and therefore, if it were a function, what would it spit out? Would it say, here's your number, infinity? It actually would just say, I don't have any answer for you. I'm not going to give you anything because I tried to give you infinity too big. Well, the limit is also coming out to be infinity, which is also, in a sense, broken. But we don't say limits are undefined so that we can distinguish between a function valuation and a limit. We would say this limit does not exist. Why does it not exist? It's just too big. It's too big. So limits must be finite answers. So in order for a limit to exist, it has to produce a finite answer. In this case, too big, so it doesn't exist. Let's look at another example. What about this one? Here's my new function, f of x. Now remember, there's a difference between evaluating the function and running the limit. Well, what's the f of c? I can't say it's infinity because over here it's saying it's minus infinity. It can't quite make up its mind, so in this case it's just undefined. What about the limit as x approaches c of my function? Well, hey, if you get on the road on the left side, it looks like you're headed to infinity. But if you get on the road from the right side, it looks like you're headed to minus infinity. Whoa, that's the biggest disagreement we could possibly have. In order for a limit to exist, you have to come at it from both sides and be in complete agreement. And that's as far away as we could be from agreement. So I wouldn't say anything here. I wouldn't say infinity or negative infinity. I'd just say does not exist because they don't agree. So anyway, there are reasons why limits don't exist. One reason is they don't agree. And if they don't agree on the graph, then you can say the limit does not exist. The second reason a limit might not exist is because, well, maybe it is on both sides headed to a special place, but that place is just too big to quantify, infinity. So we would say it does not exist when that happens as well. There is a third kind of odd case where a limit would not exist. Let's say that we looked at this function here. The function, now I'll finally actually put a function in. It'll be the sine of 1 over x. You might think this would be a regular old sine curve, but this 1 over x really causes some problems for this curve. I want you to take a look at it. So what happens is, just like any other sine, it oscillates between 1 and -1. But by doing this 1 over x argument, you're modifying the frequency of this curve. You're modifying the period as x is being changed. In fact, the frequency is being changed to such an extent that it looks something like this. It starts oscillating here between 1 and -1, but then the frequency gets higher and higher the closer you get to x equals 0, until finally the frequency just goes crazy and it just starts banging in between 1 and -1 like this, until finally, guys, the frequency is infinite in there. Infinite. So you just bold that right up, and then finally it sort of settles down and starts unraveling itself again and slowing down a little bit. Okay? Until finally it sort of takes off. It does one more and then it takes off. So what do you think is going on in here? Think about something that's oscillating at an infinite speed. It's going back and forth between 1 and -1 so darn fast that I can't pin it down. So, first of all, if f of x is equal to sine of 1 over x, I guess the real question is, what's the f of 0? The f of 0 would be the sine of 1 over 0, which is the sine of infinity. That's a really strange result, because what is the sine of infinity? What is the sine? It's not infinity, because sines always go between -1 and +1, just like this one. Well, what is the sine of infinity? Imagine a sine curve that goes on forever and ever, and infinity is off the page here somewhere. So what's the sine value way out at infinity? Nobody knows. So the sine, you know, out infinity, it's oscillating, but can you pin down where it is at infinity? You can't. All you can say is, I don't know, it's somewhere between 1 and -1. The same held true in here. My y value is somewhere between 1 and -1. So the sine of infinity, the sine of 1 over 0, is just simply unknown, undefined. Therefore, the limit as x approaches 0 on this particular function, I don't know what it is, does not exist. That's another situation where you do get does not exist for a limit. Now, the last thing I'll leave you with is actually the beginning of this chapter, and that's how do you calculate limits numerically. We're not doing analytic solutions yet where we're using mathematics. We're just saying, can we just plug things in to our function and determine what the limit ought to be? Now, I have a pretty good example of this. Let's try this particular curve. Now, functions are to be evaluated the way they are written, and this particular function is written this way. And I would love to know what the f of 1 is, and then I'd also like to know what the limit as x approaches 1 on this function is. Now, to do the f of 1, it's simple substitution, so we'll plug it into the function and find out. The f of 1 is 0 over 0. It is definitely undefined. Now, it's not necessarily undefined because it's infinity. This is that strange undefined case where is the answer 0? Is the answer infinity? Or is the answer 1? It's actually none of the above. It's just simply undefined. Now, just because the function's undefined does not make the limit undefined. Remember, limits don't care what the function value is at that particular x value. You want to answer the question, where were you headed? Well, one way to do this is to build a table. Now, we already know on this particular xy table what goes on here. At 0, y doesn't really give me an answer. It's undefined. So that's not going to help me. But what you can do is look at some nearby neighbors, like 0.999, and over here, how about 1.0001? Let's just do 2 zeros here. 1.001. Looking off to the right here, maybe 1.01, and then 1.1, and we could even go larger than that, maybe 1.25. Back here, how about 0.99? And how about just 0.9? Now the thing is, just because the function is undefined where you want to operate the function doesn't mean it's undefined for these other x values. In fact, it works just fine. So you can plug these in. In fact, if you have a graphing calculator, you can use the table feature to really quickly calculate this xy table. Let me show you how to do that. So if we go to the graphing calculator, if you go to y equals, you can type in the function that we just looked at, which is x cubed minus 1 divided by x minus 1. So type that in. You can come up here to the table feature. It should be right up here. Actually, let's go to table set first. Table set, I want my independent variable on asks. So it'll ask me for the x values. Okay, second function table. If there are any entries in there, let's hit the delete key and get rid of them. They're gone now. So what x's was I interested in? 0.9, 0.99, 0.999. We were interested in 1, but that just doesn't seem to work. 1.001, 1.01, and also 1.25. Those were all the x values I was interested in. Look what it did for me. It calculated all the y's for me. So I'm going to take those y values and plug them in here to my table. So at 0.9, the calculator computed 2.71. At 0.99, the calculator computed 2.97. At 0.999, the function behaved and calculated 2.997. Now let's go over here to 1.001. My function gave me back a 3.003. At 1.01, I got a 3.03. At 1.25, I got a 3.8125, and I think I missed 1.1, so I'll put that in the calculator now, and I get 3.31. I missed that one. There we go. This is called evaluating a limit numerically. And we'll finish with this. Now, remember what I said about limits? They really don't care what the function value is at the point of interest. In this case, the point of interest is x equals 1, so I do need to fix that. That goes here. Sorry about that. So at x equals 1, the function misbehaves. But the real question is, where were we headed in the y direction? As we came at x equals 1 from the left side, the y value seemed to be increasing and heading to 3. As we came at x equals 1 from the right side and decreased x, it looks like y was also decreasing and heading to 3. So this is what I would probably say about such a thing, that the limit as x approaches 1 on this particular function, even though the function misbehaved, this table reveals to me that all roads led to 3. It just didn't work there. The function didn't work there. So limits are powerful. Limits kind of reveal a hidden answer. Remember when we were doing the slope of the tangent line and I kept getting this 0 over 0? It didn't work. Well, there was an answer hidden in there, and limits will allow us to get to that answer. Now, on that particular table, if you looked at the table and this increased to 3, and let's say this decreased and it looks like it was headed to 5, Coming at it from the left goes to 3. Coming at it the right goes to 5. Sorry, those aren't in agreement. And I would have to say the limit does not exist. So we're going to continue with this notion of limits. We've done it graphically. We've done it using a table. Even though the function doesn't work at that particular x value, you can use the nearby neighbors to kind of infer what would the function have said if it were actually behaving and continuous there. And it's revealing that to us. Graphically, we can do the same thing. Remember these words, where was I headed? The next chapter will be section 1.3. We'll evaluate limits analytically. Analytically means we're going to use some mathematics. We're not going to use a visual graph. We're not going to just calculate a few numbers. We're going to use some mathematics behind the scenes to actually get to the exact answer for a limit. And yes, these will be answers where the function doesn't work. So the function can't just give you the answer right away. So tune in to that video shortly. Thanks.